This video lesson will serve as an introduction to Chapter 15 and will cover aqueous solutions and concentration units. So just some quick vocabulary. Remember that a solution is a perfectly mixed homogeneous mixture, meaning that in all parts of the solution there are equal concentrations. No part is different from any other part. We're going to divide the solution into two parts. There's the solvent. And the solvent is the thing that does the dissolving. It's usually the material present in the largest amount, meaning volume. In our case, most of our solutions are going to be aqueous, so our solvent is water. The thing that is dissolved is called the solute, and that's usually present in a smaller amount. So for example, salt water, the solvent is water, the solute is salt, NaCl. And you guys are used to this symbology right here, where we have a subscript after a reactant in a chemical equation that says AQ. That means it's aqueous. It's the phase of matter is in aqueous solution where water is the solvent. But there are a number of other different kinds of solutions. We're most used to dealing with this one, the solid in a liquid, salts, other things dissolved in water. But we've also talked about metal alloys as perfectly mixed solutions. But even the air that you breathe, is 80% nitrogen. And most of that remaining 20% is oxygen. So we can consider nitrogen as the solvent and oxygen as the solute. You can see there's plenty of other examples. For example, here's one. Gasoline is usually a mixture of hydrocarbons. You're used to hearing about octane, but it's dissolved in other hydrocarbons. So there are plenty of other examples other than aqueous solution. Now, the process of dissolution is an umbrella term. The process of dissolving is called dissolution, but we have learned that ionic compounds, ionic solids, do something special. Anions and cations in solution, they don't dissolve, they actually dissociate. Remember, they are actually separate particles, the anions and the cations, that are held together through the force of electrostatic attraction of the positive and negative charges. So if they are separated, they can move independently in solution and, as you know, act as an electrolyte, carry an electric charge in solution. Why does this happen? If ionic bonds are stronger than covalent, and in fact the strongest class of bonds, why are they so easily separated by water molecules? Well, the reason is a process called hydration. And hydration occurs when the ions in solution, let's take the water molecules, which are polar. Remember how polar water is. Will surround ions on their polar sides. So let me just reveal this picture here. And this shows salts. So for example, the chloride ions might be the Cl-. Notice they're much bigger than the sodium cations, which are much smaller, shown in the gray. And they get surrounded by water. Now notice when they are hydrated, as shown here, the anion, the chloride, is surrounded by the positive ends, the hydrogen-bearing ends of water. And the cation, in similar fashion, but opposite, the cation, in this case the sodium cation, is surrounded by the negative sides, the negative polar ends of the water molecule. I can show you something here very quickly. Let's go take a look at a YouTube video with this idea.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
So that is the process of solvation, or also known as hydration. Now back to class notes. Water will also dissolve water dissolves ionic compounds, and that's because water, of course, is polar and is attracted to things that have charges. That will also mean that polar water will dissolve other polar covalent materials. So the great example is sugar. We know that sugar dissolves in water, and sugar is, of course, sucrose, C6H22O11. And remember, those oxygens, the presence of those oxygen atoms, make polar groups on the molecule. Remember the big four polar, highly electronegative atoms on the periodic table, Funkel, fluorine, oxygen, nitrogen, chlorine. Where those atoms are present, there will be a slight negative polarity to the molecule because of their electronegativity. So if a molecule has what's called a polar group, shown here, then it will be dissolved by water. So let me give you an example. A great example is alcohol. Alcohol is ethane. Let me reveal this. Is ethane with an OH group. And the OH group is not the OH minus ion. It is not the hydroxide or hydroxyl ion. It is a uncharged group as part of a covalent molecule. But it does lend some polarity to the molecule because of the presence of that oxygen. And because it's polar, it's easily dissolved. So when we take the ethane molecule, when you take the OH group, bear with me, when you take the OH group right here and you add it to a hydrocarbon, remember hydrocarbons, strictly carbons and hydrogens, are non-polar, you make it an alcohol. So for example, so let me reveal this. The ethane molecule is C2H6, totally nonpolar. Remember, there's not a significant electronegativity difference between the carbons and the hydrogens. And they're also equally distributed in 3 dimensions, so there's no polarity to the molecule. If, however, we take just one of those hydrogens and we remove it from the molecule and instead put in this polar OH alcohol group, all of a sudden we're introducing some polarity to the molecule. So note what's shown here, the partial negative near the oxygens, the partial positive near the hydrogen, and now we have a polar group. And there may be a nearby water. Water is also polar and is attracted to the partial negative, the partial positive of the hydrogen and the partial negative of the oxygen. And so the ethanol molecule forms some attraction to water and therefore is polar. So we go from a totally non-polar molecule, just by putting an oxygen in the group, it becomes polar and then becomes soluble. So hydrocarbons generally are insoluble in water because they have no polar groups. But here is shown pentane, which is, of course, penta, C5, so here's 5 carbons. If we remove one of these methyl groups, let's get rid of that, and instead, once again, substitute an OH minus. I'm sorry, that's not an OH minus, it's an alcohol group, OH, okay? Then the group becomes polar. And 1-butanol, so butane is 4 carbons, butanol is soluble in water. There's a saying in chemistry, like dissolves like. What that means is that things that have similar polarities dissolve each other. If they have dissimilar polarities, they will not dissolve. So this leads us into the concept of miscibility, another vocabulary word. 2 miscible solvents are 2 liquids that are fully soluble in each other. There's no limit to the solubility. And a great example, again, is ethanol, ethyl alcohol, and water. There is literally no limit to the solubility of ethanol you can pour into water. And that's, once again, because they are both quite polar. So they mix well in each other. Of course, if there's miscible, there's something that's called immiscible. And immiscible liquids are 2 liquids that do not mix at all. And normally that's because of big differences in polarity. The great example of an immiscible two immiscible liquids are oil and water. And you guys know what happens when you take a look at, for example, oil and vinegar salad dressing. Vinegar is mostly water, and the oil, of course, floats on top before you mix it up, and the oil sinks to the bottom. That's because, yes, in part because of a density difference, but also in large part because of the polarity difference. They do not mix at this interface because they have big differences in polarity. And once again, like dissolves like, and because these have very different polarities, they do not mix well in each other. And this leads to some phenomena you've seen before in nature. For example, after a big storm, you see this coming out of the parking lot. That's oil floating on water, just like you see in salad dressing. And it's because of their polarity differences that they don't mix so well. So do remember the term like dissolves like, because it does help describe how things dissolve in each other. So this leads us to the concept of solubility. How soluble, how much do certain things dissolve? Well, there's a limit to how much a solute can dissolve in water. And of course, that does depend on temperatures. Most solids, and I need to emphasize that, most solids will increase in solubility with increasing temperature. You guys know this. If you want to dissolve some more sugar into water, you heat it up. Let's take a look at a chart here. This shows solubility in grams per 100 mils of water, shown on the left. And down at the bottom of the scale on the x-axis is temperature. And as you can see, most materials on the chart have some sort of a positive slope. As temperature increases, solubility increases. But that's not the case for everything. There's a couple of weird things going on here. For example, salt seems to have, no, that's wrong. It's this one here. I don't know what's going on with cerium sulfate. I could have to do a little more research to figure it out, but there's something strange. Most things, though, most solids will increase, or solubility will increase with temperature. So this idea that solids are more soluble at high temperatures is exactly the theory behind the way we make rock candy. Now, rock candy is not glucose. In fact, it's sucrose. But glucose is a pretty good analogy. Remember, sucrose is two glucoses stuck together by a dehydration synthesis reaction. In any event, you can see how glucose gets incredibly soluble with increasing temperature. In fact, we need to extend this line almost off my charts, in fact, way off my charts, to get up to beyond the boiling temperature. All right. Boiling is at 100 degrees C. So here's the boiling temperature right here. I'm going to do this roughly. And I looked up the values of the solubility of sucrose at 20 degrees C. So at 20 degrees C, right here, sucrose has a solubility of about 180 grams per 100 mils. Okay. At boiling, sucrose is roughly 500 grams per 100 mils. That's remarkable, by the way. 500 grams of sugar can dissolve in 100 mils or 100 grams of water at the boiling point. So here's how you make rock candy. You boil water and you dissolve the maximum. And the maximum at boiling is 500 grams. And then you cool it down. So we're going to, in green, we're going to cool it down to room temperature. And room temperature is about 20 degrees C. And the amount of sugar that can be carried by that water must decrease from 500 grams down to 180 grams. So a whole bunch of sugar, in fact, a little more than 300 grams per 100 mils, must come out of solution when you cool it down from saturation at boiling. So where does it go? Well, if you hang a string or dangle a popsicle stick or something like that into the water, it'll precipitate, it'll crystallize out onto that popsicle stick, and there you have rock candy. So it's really quite simple, an application of the principle that things become, at least soluble solids become more soluble at hot temperatures than and become less soluble at cool temperatures. Now gases, unfortunately, do exactly the opposite. Gases will decrease in solubility with increasing temperature. So take a look at this chart here. Gases all have a negative slope. So as we increase temperature from left to right, the solubility of a gas will decrease. So all of these gases have a negative slope, decreases with increasing temperature. And you guys have actually seen applications of this before. When you boil water, notice this is not boiling yet. It's not at 100 degrees C. There will be some bubbles that form on the inside of a flask before it's boiling. That's because the temperature is increasing, so the gas becomes less and less soluble with increasing temperature. So these bubbles start to form as gases come out of solution. This is also, for you trout fishermen out there, the reason that trout live in cold water. It's not because they can't tolerate warm water, it's because they can't tolerate low oxygen temperatures. So this doesn't look like a big change in the scale here, but at temperatures close to freezing, oxygen is twice as soluble as it is at room temperature, right down here. So most trout thrive in around 12-degree water. That's because they need higher oxygen levels than warm water species like bass and carp. All right, there's your fishing lesson for the day. So I just mentioned a word called saturated. A saturated solution is one that contains the maximum amount of solute at that temperature. No more can dissolve. And we sometimes call this the solubility limit. We've come into contact with that before when we talked about precipitate reactions, where things that were slightly soluble produce more product than can be dissolved, so the rest comes out of solution. It's exceeded the saturation level. Then there's a thing called unsaturated, which of course means that the solution has not yet reached its saturation limit. So you can dissolve more at a certain temperature. Finally, there's an unusual circumstance called supersaturation. And a supersaturation is an unstable situation where you've actually dissolved more solute than you normally can at a certain temperature. It has to be done very carefully in controlled circumstances with not a lot of vibration or dust that can contaminate the solution, because it will crystallize out. But here's a quick video that shows some fun you can have with supersaturated solutions of sodium acetate. I don't believe there's any sound on this one, but here's what the solution looks like. It's a clear solution, but if you introduce any disturbance to it, the material starts to crystallize out immediately. And you can see that forms a solid here. There's so much dissolved in solution that it forms a solid, and you can see it gets warm when you do that. And there's a reason. We'll do a demo of this next week, and we'll talk about why this is exothermic, why it gives off heat. But there's some fun things you can do with sodium acetate. There's the solid material after it's crystallized. Forms a hydrate, by the way, a dodecahydrate. So there's no surprise that it encapsulates all the water inside its crystal structure. And you can do fun things like pour towers of it onto the seed crystals, and it solidifies. And if you're very tricky about it, I think that's shown next, you can hold the flask as it pours out, and it'll crystallize into the flask. Here we go. That's what's going to be shown here. Anyway, you get the idea. I'm going to pause that. And we'll go back to class notes right here. Moving on. So now we need to talk about concentration units and how we do some calculation work with concentration. So first of all is sort of an old school unit. It's not used much anymore except in food science, where you might be familiar with some terminology that says contains 30% of your allowable glucose or 40% of your daily intake of protein. So mass percent is often used in foods. It's one way of measuring calculations. Another example, vinegar, by law, we're going to learn about this later, by law, believe it or not, must contain 5% acetic acid. So that percent is a mass percent. So remember, percent always means part over the whole, and that's what mass percent means when we're talking about solutions. The mass of solute, remember the solid that is dissolved, the mass of solute present divided by the total mass of the solution. So it might look something like this. Here's a red box formula. You got to know how to do this, right? Mass of solute divided by total mass of solution. Remember, the solution contains two parts, so total mass of solution will include the mass of the solute and the mass of the solvent. And of course times 100 because we're talking about a percent. So let's do a couple of examples of this. Here's the first one. Let's say we dissolve 67.1 grams of calcium chloride in 300 mils of water. What's the percent by mass of calcium chloride? Well, remember, it's part over the whole. So it'll be 67.1 grams divided by the total mass, which is 67.1 of the calcium chloride, and 300 grams of water. And when you do that math, you get approximately 18.3%. Okay, so again, just part over whole, but remember to include the solvent. Let's do another one. How about an alloy? So we've got an alloy which is some iron, a little copper, and a little zinc. What's the percent mass of zinc? Well, zinc is 4.03 grams. So the percent mass of zinc will be 4.03 grams over the total mass, which will be 4.03 plus 145 grams of iron, plus there's a little copper in there, 5.31. Of course, times 100. I think I forgot that on the last slide. And that's going to be equal to about 2.61% zinc. Okay. Another much more commonly used unit of concentration, especially in chemistry, is molarity. And molarity, red box formula, molarity is moles per liter. It's a simple division problem. Moles divided by volume in liters. And so you've seen this whole year, you've seen us use solutions with certain concentrations written on the bottle, and it might say 2.4 mHCl. Well, that means 2.4 moles per liter, or the molarity is 2.4. And that's all it is, moles of solute per liter of solution. And there's a little calculation involved, but it's simple. You may have to do the old mass to moles conversion, and I hope you remember how to do that. We'll practice a little bit, but first you've got to find number of moles, so you may have to convert mass to moles, and then of course divide by the volume, but in liters, so be careful, don't divide by milliliters. So here's another example. Let's say we have 25 grams of salt added to 200 mils of water. Calculate the molarity. So we're going to have to do a little bit of math on this one. So we've got 25 grams of salt, okay, and we're going to convert that to moles. So we're going to divide by the molar mass. The molar mass of salt is 58.44 grams, okay, per mole. So this, of course, remember that grams are going to cross out. We're going to be left with moles, and then we want to divide that whole mess by the number of liters we have. But be careful, we've got 200 mils, that's 0.2 liters. So now we're left with moles per liter, and when I do that math, I end up with approximately 2.14 molar NaCl, and that's the answer for that. Let's do another example, and this one's a harder one. What if we got vinegar? Now vinegar is 5% by mass acetic acid, and which means it's 95% water. What's the molarity of vinegar? What's the number of moles per liter? Well, I need to give you some information to solve this problem. First of all, I have to give you the density because we need to assume a mass of, if we're doing percent by mass, if we're doing percent by mass, I have to assume a mass of solution to start with. And the other hint is that we're going to assume 1 liter. Okay, so that's the starting point. So here we go. 1 liter, remember that's equal to 1,000 milliliters. Okay, and I'm going to convert that to mass immediately. So I'm going to multiply it by the density, which is 1.01 grams per mil. Okay, so now I'm going to have some number of grams. You can see, of course, that milliliters are going to cross out. Okay, I'm left with some number of grams, and I want to, and 5% of that mass. So I've got a liter, it weighs some amount, but 5% of that, okay, or 0.05 is the acetic acid. The rest of it is water. So now I've got mass of acetic acid, and we're going to convert to moles of acetic acid. So we have to divide by the molar mass. So a mole of acetic acid is given to you here, 60.1 grams. And once again, look at what crosses out. Grams crosses out here, and we're going to be left with moles per liter. Okay, or actually number of moles, but that is in 1 liter, which we assumed at the beginning, and that is equal to 0.84 moles, and we said that was in 1 liter. That was our assumption at the very beginning. So the molarity is 0.84 molar for vinegar. That's a harder problem. In the previous 2 examples, you were given grams of a solute and volume of solution, and you need to convert from mass to moles divided by liters to get molarity. Well, what if you were given molarity and you're given the volume of solution? You needed to calculate the mass of solute dissolved in that material. This is essentially going in the opposite direction of what we just did, and it's not difficult. So remember that molarity, that's capital M molarity, is equal to moles divided by liters. What if we just take that and we multiply by the volume? In other words, we take the concentration, moles per liter, and we multiply by liters. You can see that the liters would cross out, and you'd be left with the number of moles. So that's equal to number of moles, and that's of course easy to then convert moles to mass. So we can simplify this a little bit by just saying M times V. So molarity divided by moles per liter times liters is equal to number of moles. All right, and that is a red box formula for you right there. Just remember that if you need to figure out the number of moles of solute in a solution, you just take the molarity and you multiply by the volume in liters. M times V is equal to number of moles. This is a really important formula for the next 2 chapters, not just this one. So let's do an example. What mass of calcium chloride is present in 40 mils of 1.5 molar solution? So remember, M times V is equal to number of moles. Okay, so we're going to take molarity, which is 1.5 molar, or moles per liter. In fact, let's write it like that, just so we're used to the units. So 1.5 moles per liter. Okay, moles per liter times the number of liters. Now be careful, that's 40 mils, so it's going to be times 0.04 liters. Okay, that's equal to 0.06 moles of calcium chloride, and then we're just going to multiply that by the by the molar mass. And I looked it up, did the calculation. It's 111 grams per mole for calcium chloride. So you can see what crosses out here. So first of all, liters over here, we're left with moles, and then moles crosses out, we're left with grams, and the answer is 6.66 grams of calcium chloride. That's your answer. Let's do one more. Same idea. Let's say, and the reason we do this is because very often you're asked in chemistry to mix up certain volumes of a certain molarity of solution. So let's say you are charged with making 250 mils of a 0.2 molar potassium nitrate solution. So you got to go over to the lab hood, measure out some mass of this solid, potassium nitrate, white crystalline solid, and then mix it into 250 mils of water. Well, what mass? That's the question. What mass of potassium nitrate do you need? Okay, so once again, we're going to use this formula. M times V is equal to number of moles. So, pardon me, we need 0.2 molarity, or moles per liter, times 250 mils, convert to liters, times 0.25 liters is equal to 0.05 moles of the potassium nitrate. And then of course we're going to take this value and we're going to say 0.05 moles of potassium nitrate times the molar mass, and the molar mass is 101.1 grams per mole. That's going to tell us the number of grams, and it's approximately 5.06 grams of potassium nitrate, and that's how much we'll have to mix in to the 250 mils of water, because we had that right here, to get a 0.2 molar solution. And when you actually go to do this, there's some steps involved. We'll do this in the lab, but you first of all mass the solute. That's obvious. So from our previous example, we'll have to mass out 5.06 grams of potassium nitrate, and then we'll add to a volumetric flask. Now remember, a volumetric flask is a precision instrument that has a little mark on it at the, in this case it would be the 250 mil mark, because we were talking about a 250 mil solution of potassium nitrate. So these are precisely measured out pieces of glassware, very carefully calibrated. So let's say we measure out our 250 mils. So here's our 5.06 grams. So there's our potassium nitrate. And then we start to add some water. And what you actually do is you don't fill it up to the line immediately and then walk away. What you actually do is you fill it up part way. So I'll fill it up. Actually, what I'll do is I'll fill it up to more like 2/3 or almost full. And I'll let the stuff dissolve. I'll let it sit there for 15, 20 minutes, sometimes even overnight. And then I'll top it off at the very end. I'll add water to the volume mark shown here. Okay. The reason we do that is because there's an interesting thing called a volume defect, that occasionally when you add highly ionic compounds like potassium nitrate to a solution, water becomes so attracted to those ions in solution that it actually changes volume. So by adding a solute, water can shrink down in volume from 250 mils of added water to 248, and then you don't have a proper concentration. So you account for that by adding the solute first, giving some water and letting it sort of settle out, equilibrate, and then topping it off at the very end up to the top mark. And even at that point, I'll let it sit usually overnight to make sure I've got the right volume. And I will show you a demo of this. And so ends our class notes for today. So good luck and get started on your problem set. Cheers, and I hope to see you tomorrow.